Level 1 got you writing working Go variables, control flow, functions, basic error handling. Level 2 is about writing Go that other engineers actually trust, methods that behave predictably, interfaces that decouple your code, errors you can inspect instead of just print, safe concurrency, and tests that catch regressions before your users ever see them. Go has no classes. Instead, you attach behavior to a type by writing a function with an extra parameter up front, the receiver, before the function name. That one idea, receiver syntax, quietly explains almost everything else in this section, so it's worth getting comfortable with it now. Here, area is declared with our rectangle before the function name. Calling rect.area is really just calling area with rect passed in as an argument. Receiver syntax is sugar over an ordinary parameter, nothing more. A value receiver gets a copying broken increments that copy and then throws it away, so the counter never actually moves. Switch to a pointer receiver, and inc modifies the real struct sitting behind it. Use a pointer receiver whenever a method needs to mutate state, like this accounts deposit and withdraw methods. And once one method on a type needs a pointer receiver, keep them all. Pointers mixing value and pointer receivers on the same type gets confusing fast. This is the rule that trips people up. If area has a pointer receiver, only a pointer to square satisfies the shape interface. The plain value doesn't have that method in its method set at all. Pointer receiver methods can even be called on a nil pointer safely. This recursive lists len method returns 0 on a nil list instead of crashing, as long as the method checks before it dereferences. Method sets decide who satisfies an interface, which is exactly where we're headed next. Go's interfaces, and the implicit way types satisfy them without ever mentioning the interface's name. An interface in Go is just a named set of method signatures. Any type that has those methods automatically satisfies it. No implements keyword, no inheritance, no registration step required anywhere. Rectangle and circle never mention shape anywhere in their code. There's no implements keyword to write. They satisfy the interface just by having area and perimeter methods, and you could define shape in a completely separate package months later and both types would still qualify. The standard library's most useful interfaces have exactly one method. Implement string here, and temperature prints itself correctly anywhere println or a %v format is used, without any extra plumbing. Here's the classic Go gotcha: an interface value is really a type and value pair. Return a nil pointer of a concrete type as an error, and the interface itself is not nil, it still reports a failure that isn't really there. A type switch lets you branch on the concrete type stored inside an interface. Inside each case, the variable already has that case's type, no extra assertion needed to use it safely. Interfaces compose out of other interfaces. Read closer here is just the union of reader and closer's method sets, exactly how io.readWriteCloser is built in the standard library itself. Error, which you use in nearly every Go function, is itself just an interface with a single error method. That's exactly where custom error types and wrapping pick up next. A plain error string can't be inspected reliably. Comparing error.error against a literal breaks the moment someone rewords the message. Go gives you two much better tools instead: sentinel errors for fixed, known conditions, and custom error types for errors that need to carry real data. Sentinels are package-level error values declared once and returned everywhere that condition happens. Callers check with errors.is, never by comparing error text directly, which breaks the moment a message changes. When an error needs to carry data, which field, which value, which rule define a type that implements error. Errors.is then pulls the structured validation error back out for you, not just its text. The %w verb in fmt.errorf wraps an error instead of replacing it. The new message includes the old one, but the original stays retrievable. Each layer adds context, reading config, then startup, while errors.is can still find the root cause all the way at the bottom. Errors.is asks whether a specific error value appears anywhere in the chain. Errors.is asks whether an error of a given type is in there. An unwrap method is what keeps that chain walkable at all. Since Go 1.20, errors.join combines several failures into one, so you can validate every field and report all the problems at once instead of stopping at the very first one you hit. You now have errors you can inspect instead of just print. Next, we bring in Go's other headline feature, Goroutines and channels for real, lightweight concurrency. A goroutine is a function that runs independently, scheduled by the Go runtime instead of the operating system. Starting one costs almost nothing, which is why Go reaches for concurrency far more casually than most other languages do. Put Go in front of any function call and it runs concurrently, right alongside everything else. But remember, when main returns, every goroutine still running gets killed instantly. There's no automatic waiting. Time.sleep is never the real answer in production code. A wait group counts down properly, call add before launching each goroutine, done when it finishes deferred, so even a panic still decrements and wait blocks until everyone has checked in. A channel is a typed pipe that carries values between goroutines and synchronizes them at the same time. An unbuffered channel is a rendezvous point the sender blocks until a receiver is actually ready. A buffered channel gives you a queue with real capacity, sends only block once it's full, receives only block once it's empty. Use one when a producer legitimately runs ahead of its consumer, not to hide a bug. Select waits on several channels at once and proceeds with whichever is ready first. If more than one is ready, it picks randomly. Adding a time.after case gives you a clean, built-in timeout instead of hanging forever. Channels are the idiomatic default, but a sync.mutex is simpler for guarding shared state, like this counter. Run any concurrent program with Go run-race to catch bugs like a missing lock reliably. Concurrent code is exactly the kind of code that's easy to get subtly wrong, which is why testing it properly matters more than ever. Let's close with Go's built-in testing package. Go ships with its own test runner and testing package built directly into the toolchain. No framework to choose, no assertion library to install, no config file to write. Name a function, test something in a file ending in _test.go, and Go test finds and runs it. Go has no assert equal you compare with a plain if and report with t.orf. The idiomatic message format is func of input equals got, want expected, so a failure reads clearly without opening the source. Table-driven tests are the dominant style in Go, including inside the standard library itself. List your cases in a slice, loop over them, and call t.run for a named subtest. Adding a new case later is just one more line in that slice. Because Notifier depends on a small sender interface instead of a concrete SMTP client, you can test it with a fake that just records calls. No mocking library required anywhere in the project. Double equals doesn't work on slices or maps. Slices.equal and reflect deep equal do, and it's worth knowing an empty slice and a nil slice compare is different, so decide deliberately which one your function returns. That's the full arc: methods that behave predictably, interfaces that decouple your code, errors you can actually inspect, safe concurrency, and tests that catch regressions early instead of in production. That's 5 lessons from Go's intermediate level, each one free with runnable code you can copy and run yourself. Links to all 5 are on screen now, in the exact order we covered them today. Go build something idiomatic.